So today, I'm very happy to introduce the very interesting researcher. Then let me introduce him, and then we can start the talk. So, the Dr. Koya Narumi is a project assistant professor in the Department of Electrical Engineering and Information Systems, Graduate School of Engineering, so the University of Tokyo, and he received a PhD degree in the information science and technology from the University of Tokyo in 2020. Then his research interest life is in the human-computer interaction and also computational fabrication, leveraging the property of the novel materials and structures such as the phase-changing soft actuator, self-healing interface device, and then inflatable mobility devices. So his work, he also works as a program committee and the organizing committee of the HCI conferences, such as HCI and UIST. So overall, his research and the topics is very much of some many interesting material interactions, and also a computer-human interaction. And also, he is a very legend of this research community, and he's also working on the not only Japan but also very internationally outstanding research. So that's a short introduction, and I'm very happy to introduce Koya, and then please start the talk. Thank you.
Yeah, thank you so much for such a great introduction. So I'm Koya Narumi from the University of Tokyo, and today's topic is origami-inspired computational fabrication. And my topic is, just as you see, fabrication. And I'm not sure how many people are interested in this kind of topic, because OIST focuses more like natural sciences or something else. But maybe some of you guys have something to bring out from my topic, because this is about origami. So let me first introduce myself. So I'm Koya, and I actually entered the University of Tokyo as a bunke. I mean, I was specializing in history or law, but sometimes I changed my mind to somehow go to the electrical engineering. And now I graduated, and I don't know why, but I'm now working as a project assistant professor in the University of Tokyo. And my hobby is riding on a motorcycle. So 3 days ago, as soon as I arrived at Naha Airport, I decided to hire a motorcycle and went to the beach. And somehow there are 3 riders who invited me to go to so many places just in the midnight. So Okinawa is such a great place to visit. And about the research topic, my topic is computational fabrication, but in more broader sense, my topic is about human-computer interaction and computer graphics or soft robotics. And this is maybe the takeaway of my talk. So I usually design daily products like clothes we wear or food we eat or mobility devices we ride by computationally distributing special materials and structures. And not only the design, but I also fabricate them with digital fabrication tools like 3D printers or laser cutters, and try to create the new experiences using such kind of fabricated objects. So let me start the topic. So what is the computational fabrication? So I don't think this is a really well-known terminology, but actually this was generated in 2010 or later. So this is a combination of computational design and the digital fabrication. So computational design is a notion in the computer graphics to design something using a mathematical optimization. So for example, if you try to design a name card, you should decide how large the font is or what color you use. But this kind of things is usually done by human sense. But computational design tries to optimize such kind of human factors. And this is about the design. And after 2010, we can use a lot of digital fabrication tools to embody such kind of digitally designed objects into the real object. So I think the computational fabrication refers to the fabrication of computationally designed objects, but under the constraints of the real tools or real materials or real structures. So recently, a lot of people are trying to work on computational fabrication. For example, after 2016, there is a new conference called ACM SCF, Computational Fabrication Symposium, or there is also a series, online fabrication seminar series from 2021. And even in the conferences like CHI or UIST, there are tons of papers about fabrication. And maybe, I don't know who are interested in this kind of thing, but there is a book about computational fabrication. I think this is only the book about the computational fabrication, and it is really amazing that this is written in Japanese. So if you're interested in my topic, maybe you should refer to this book. This is really easy to read. So this is the summary of what I did in the past. For example, when I was an undergrad student, I was working on a conductive ink pen with which you can write the circuit or erase the circuit. And after that, I also worked on the soft robotics. For example, in the top row, there is a butterfly. And if you hover the butterfly on the hot water, it will change the shape by the heat. Or I also work on the fashion design, for example, by using the soft actuator, we design the clothes by actuating by itself. And after 2020, I was mainly working on the origami-related fabrication, which is the topic of today. So because if I try to talk about these kind of things, it'll take maybe more than 2 hours. So today I'm gonna focus on the 3 topics, which is about origami. So the first topic is pop-up print. This is about origami plus 3D printing. And the second topic is crane. This is origami plus design. And the third topic is inkjet 4D print. This is about origami plus fabrication. So let me start by the pop-up print. So if you have some experiences of 3D printing objects, maybe you know the biggest issue of printing tall object or a large object. If you try to make something big, then you should suffer from the longer printing time or larger supporting materials consumptions. So usually, if you try to 3D print a complex object, you need to print the supporting material as well as the main materials. And such kind of materials will be thrown away after the fabrication. And if you try to prototype something, you should print a lot of objects, and then maybe you should suffer from the storage space. So in general, the smaller the object is, the better for 3D printing. So you should print something as small as possible. But if you try to, so when I was suffering from these kind of issues, I found one interesting topic about the biology, which is called inverse origami of beetle's chrysalis. So it is known that the beetle has a folded horn, even inside of the chrysalis. And after they become an adult beetle, they inject a kind of resin-like materials into the folded horn to make a really larger shape. So this is called inverse origami. So my idea is if you try to print a larger object, maybe we can first of all print the folded structure, and then you can manually push it or pop it to make a larger object. So this is a pop-up print. So this is the Japanese tokuri and ochoko printed in the folded state. And because this is watertight, you can enjoy Japanese sake. And we started by this kind of simple shape, or we can also print this kind of triangular shape, or maybe doubly curved shape, or I don't know why I made this, but this is also one of the shapes I made. And you can actually input any shape like a bunny. And this is the GUI software in which you can visualize which part can be foldable. And after designing the folded shape, you can download the STL file for the final shape. Or sometimes the shape is super complicated and you cannot fold it. But in that case, you can slightly modify the shape so that it can be folded into this kind of, this kind of shape. So this is the overview. So as an input, you should input the STL file. This is the really maybe most famous file format for the 3D printing. And then the system visualize the red part, which means the foldable area. And then the system automatically fold the shape into the folded state. And finally, the system automatically thickens the material because all the 3D printed materials need a thickness. And the system also distributes materials. So some part needs to be really flexible. In this case, the black part is flexible and the other part is a rigid part. So if you try to fold the 3D objects, we need to think about two things. One is how to extract the tapered region. Tapered region means the foldable region. And the second problem is how to apply planar folding. Planar folding means just iterate the mountain fold and the valley fold again and again to make it foldable. So let me start by the tapered regions. So first of all, in order to fold something, we need to find the tapered region. To do so, we first of all prepare for the two planes, two coplanar planes, and define the z direction. And if all the region, if the normal vector, if the z factor of all the normal vectors have the same signs, for example, all the z factors have a plus, then the shape has a tapered shape to the top side. And if the z factor have a minus to all the regions, maybe the shape is the inverse triangular shape. So, but in reality, many of the materials is not tapered. Tapered. In this case, for example, the bunny has a tapered shape, but at the tail, this is gonna go to the other direction. So this is not the tapered shape. So in this case, we can slightly modify the shape so that it can be foldable. So to do so, first of all, we extract the cross-section of the materials and project it to the same plane. And if there is some intersection, this means the structure is not tapered. So we slightly move the vertex of the intersection. And after all the intersections are diminished, maybe this is self-foldable, not self-foldable. This is tapered and foldable. So we can make any tapered region using this kind of method. And then we apply a planar folding to make it really foldable. So this looks really easy task, but this is the bad example of my friend trying to imitate my pop-up print. So this looks like good, but if you try to expand it, the structure goes back if you leave, if you leave the hand. So the problem is, even if you fold the shape, if the structure is not bistable, the structure cannot sustain the shape in the unfolded state and the folded state. So I don't talk about any detail of this calculation, but we actually printed a lot of samples and derived the equations to make it bistable. So this is the software. So as I said, if you input the STL file, you'll see some colors on the input shape. So the red shape means this part can be foldable. So if you click the red part, it will be automatically folded. And the green part means this is already folded. And blue part is not foldable. And you can also rotate the STL file so that you can find your satisfied shape. And if you drag, for example, the tail of the bunny, you can slightly modify the shape so that it can be foldable. So in the introduction, I said, this is done because I wanted to make it, I wanted to print this with a smaller printing time, smaller materials consumption, and a smaller storage. So in the best case, for example, the printing time and the supporting material consumption decreased to 1/5 of the original structures. For example, in case of the Tokuri, I'm sorry, my eyesight is really bad. So in case of Tokuri, printing time reduced to 5 hours from 10 hours, and the supporting materials consumption decreased from 400 grams to the 300 grams. So this is a kind of sustainable fabrication. And after this project, I more dug into this kind of sustainable fabrication direction. So this is the really short introduction, maybe short summary of the pop-up print. So the next topic is more mathematical, I think. So this is called Crane. So this is the origami design software to achieve a functional, foldable, and fabricable origami project. And we did this project in collaboration with the company Nature Architects, which tries to achieve mechanical metamaterials, which is a really special structures in academia, but maybe, I don't know. Okay, let's go. So in HCI, in human-computer interaction, a lot of people are recently interested in fabrication with some origami structure. For example, in 2013, Stephanie Miller achieved making an origami structure using a laser cutter. So she didn't cut the structure using a laser cutter, but just melt the plastic film or plastic board to fold the hinge. And later on, a lot of people are more and more interested in making an origami structure using digital fabrication tools. But I would say this kind of structure is really too easy. All the origami structures we can make with digital fabrication tools is still super easy. So if you look at other fields, for example, in the space engineering, they are using a really complex origami structure called flasher to the wings of the spacecraft, or in the garments, Issei Miyake is using this kind of super complex tessellation structure to achieve a beautiful garment structure. Oh, by the way, I'm wearing the same clothes right now. So this is also made with this kind of origami structure. And in the field of mathematics, it is proven that any polyhedron, for example, this is a pet bottle or this is a laptop, any shape can be foldable from a sheet of paper. So in this case, he's folding a bunny. So if you look at other fields, really sophisticated origami design is achievable, but somehow in HCI, they're only folding one hinge and they are satisfied with really small portion of the origami fields. So for example, as a concrete case, do you think this is easy to fold or this is easy to design? Yeah, this looks like IKEA's furniture, and it would be really easy to achieve this kind of chair design or table design. But in reality, designing this kind of furniture is super difficult because, for example, in case of chair, the chair must fold from a flat sheet into the 3D structure. This leads to the mathematical constraint of developability. Or if you look at the table must fold into a flat shape, not from the flat structure. This leads to the different mathematical constraint of flat foldability. And because this is a furniture, maybe most of the furniture has a symmetric shape, so this has to satisfy the symmetric constraint. And many people forget about the fact that this kind of furniture is made by the rigid materials, and we cannot use a paper materials. So for example, if you try to fold a paper crane, you cannot do so using a wood board because the wooden board cannot rely on the deformation of the panel. So this has to satisfy the rigid foldability constraint. And because this material is really thick, we have to think about the self-intersection or hinge intersection. So this leads to another constraint of fabricability. So in short, this is so hard to design. So this is why we designed Crane. This is a software integrated design platform for functional, foldable, and fabricable origami structures. So this is a GUI of the Crane. So on the left, there is a visual programming environment. And if you place some of the components, you can visualize the final structure on the right. And now we are trying to simulate the folding structure of the 3D shape from a flat sheet. So this is implemented in the rhinoceros or grasshopper, which are really famous for industrial designers. And this is the back-end overview of the crane system. Although it looks so complicated, but the whole structure is relatively simple. So usually people start by giving input, and then people places some of the design constraints, which leads to, for example, the chair must be flat foldable, or the chair must be rigid foldable, or such kind of things. And then an integrated solver solve such kind of constraints and also find some new shapes. And after the simulation is done, the system also automatically calculates the thickness and applies the appropriate hinge structures for the desired fabrication tools. For example, if you 3D print the chair, or if you laser cut a chair, or if you mill the chair, all the hinge structure could be really different. So if you can input any kind of option to design the different hinge structures. So as an input, in this example, he tried to prototype a chair using an actual sheet of paper, because many of the origami designers usually start by the actual paper for prototyping, and then they take a picture. He took a picture, and then the system automatically translates the photo into the vector structure into the CAD design. And next, we are gonna do the simulation. So this is the simulation result of the prototyped chair. But yeah, this is foldable, but as you can see, this is really bad as a chair. Maybe this is not a chair because, for example, the seat is not horizontal at all, or maybe edges floating from the ground. So if you try to sit on this chair, maybe you'll be stumble from the chair, and the backrest leans too much, and two edges on the back do not touch each other. So these kind of situations is not really ideal for the actual chair design. So in such cases, people put the design constraints corresponding to such kind of issues. For example, on-plane constraints on A limits all the vertices on the same plane. So using this kind of constraints here can lead to the form finding a new shape. So in the next slide, there is a video which transforms really at the time. So maybe you should take a close look. So in this case, the chair design automatically changes in a second. And even after the constraints are solved, you can drag some of the vertices to modify the shape, but still all the constraints can be preserved. So you can keep some of the goals, for example, design goals, the seat must be horizontal, and you can keep updating the design process. And after the design process is done, you can fabricate the object. So far we have 5 components corresponding to the different hinge structures, which is suitable for different fabrication tools. For example, if you try to use a CNC milling machine, we can use, for example, box joints, which is really easy to fabricate using a milling machine, or you can reuse the same structure to 3D print the chair. And in this case, maybe you can start by the prototyping process using a FDM 3D printer. And once this chair looks good, you can proceed to the larger fabrication tools like CNC milling or laser cutting. So there are so many functions in crane, so I cannot talk about any details. But for example, if you input the 2 coplanar structures, the system automatically applies the repeated structure called tessellation between them. And using this, for example, you can design your own lampshade. And in this case, we automatically generated this kind of shape. And we also use the constraint of the rotational symmetry to make it really beautiful. Or the system also has a function of generating any origami structure from an arbitrary 3D mesh. So maybe this is gonna be really useful for the people in some different fields, like maybe biology. But so using this kind of system, we generated, in this case, a mask So first of all, we prepared a 3D mesh covering the face, and then the system automatically generates a fancy mask like Hokuto no Ken. This is really crazy mask. But I was really serious when I tried to build this because this kind of mask has a really large surface area, so it's gonna be better for breathing. So we were really serious when I was making this, but the reviewer said, you don't have to try to deal with COVID-19. Yeah, but I was serious. It has nothing to do with COVID. Yeah, anyway, so this is the project. This is the academic project, but later on we had a collaboration with Issey Miyake. This is a fashion brand. So we made something like this, and I'm gonna explain the detail. Oh, so this is the video explain the detail, okay.
This project was born from our cutting-edge design technology integrated with A-POC ABLE ISSEY MIYAKE's manufacturing process. Together, we explored the limits of garments made from one piece of cloth. By integrating computational design with the technology of steam stretch, a program automatically designs a pattern that meets the designer's ideal form for a garment. It also allows us to make organic shapes that cannot be made just by piecing fabric together. We developed this technology, and this jacket is an example of what it is capable of.
So yeah, in April 2023, in the last year in Milan, Italy, we were in the branch of Issey Miyake in Milan, and there is a jacket like this. And what is surprising is this jacket is foldable from a piece of fabric. So usually we make this kind of jacket using 10 pieces or more than 10 pieces of fabrics together, sewn together, but this is made by one cloth. And in this case, we use the really special pleating technology of Issey Miyake called steam stretch, and all the shapes are shrunk at once to build a 3D structure. But this kind of steam stretch technology was developed by Issey Miyake, and steam stretch itself was not developed by ourselves. But traditionally, only one designer of Issey Miyake has a knowledge to imagine how the 2D origami shape can transform into the 3D shape. And this is totally impossible for normal people to reproduce this kind of thing. But what we did is we input the 3D structure, and then the system automatically calculates the 2D structure that can fold back into the 3D structure. In this case, the designer only need to prepare for the 3D surfaces, which is much easier than designing the really complex origami shape in their mind. So except for the jacket, for example, we designed the dress or we designed a really geometric sphere, which is usually impossible to fold. And there were a lot of guests in the Milan Design Week. And throughout this kind of project, we were super proud of our paper, which was applied to the real design industry. So we actually published this paper to the conference called KAI. And in KAI, there are so many interesting projects, but really few papers go to the real industry. So we are really proud of this kind of result. So as a conclusion, so we designed a crane. This is a seamless design platform for design and the fabrication of origami products. So which allows the input simulation and find a new shape and the panel thickening for different fabrication techniques. And yeah, this is a good news. Crane is open source, so you can download the plugin in Food4 right now, or you can also refer to the GitHub for the source code. Yeah, so this is the crane. So far I talked about the 3D print plus origami and design plus origami. And the third project is fabrication plus origami, which was published in Transactions on Graphics Code, or CGraph. So this is about the self-folding or 4D printing. So I'm now printing something flat, but if you base the structure into the hot water, it will automatically change the shape into, in this case, the cap. And we can actually fold any shape like this. So as I explained, any polyhedron is foldable. So Tochi Sensei is my co-worker, built a software called Origami-inspired in 2007, in which you can input any kind of 3D polyhedron or any 3D shape, and then a system automatically calculates the 2D shape that can fold into the 3D structure. And this kind of phenomena was actually proven to be true. So any polyhedron is mathematically foldable from a sheet of paper using these algorithms. And Tochi Sensei designed a lot of complex structure. This is so good. Maybe this is a really biggest finding of origami theory, but there is a really one big problem. So the problem is origami takes a long time. Although the design process only takes 1 second or maybe 1 minute, but folding this takes 10 hours. So for example, if you look at this video, maybe you'll see the sunlight is slightly changing, the color is fading, so this is the biggest issue to make this kind of origami technique into the industry. So as a possible solution to automatically fold something, there is a technique called 4D printing. So 4D printing is a notion of the 3D printing the structure, and then if you apply some stimulus in the time-dependent stimulus, then a shape automatically changes into the pre-designed shape. So this is called a thermal, published in 2018. So this is the work of my past advisor in Carnegie Mellon universities. In this case, they calculate how the plastic will shrink depending on the speed of the printing process, and they can design this kind of rose shape. This is good. But the problem is origami designer is crazy. So the center one is the bunny designed by the Thermal project in 2018. In this case, the number of facets, number of faces was 26. But what origami researchers want is much more than it. So for example, this bunny structure has more than 4,000 of facets, and it is totally impossible to reproduce this kind of crazy origami using such kind of method. So this is why I worked on the project called Inkjet 4D print. This is about the self-folding tesserated origami objects by Inkjet UV printing. So this is a really summary of the video. So if you pour the hot water into the flat structure, it will slightly, maybe it will change its shape less than 1 second, I think. So this is how we achieved it. First of all, we prepared the shrinkable plastic film. So if you apply, for example, 70 degrees Celsius, this film will be automatically and isometrically shrink. And we print the structure. We print the origami patterns on both sides of the paper, on both sides of the sheet. And if you apply heat, then it will shrink into the pre-designed shape. So this is the basic principle. So first of all, there is a heat shrinkable sheet in the middle, which is sandwiched by the ink layers. And if you uniformly apply the heat, only the exposed region can shrink, but all the other regions is prohibited. And depending on the width of this exposed area, you can control the folding angle from the 0 degrees to the 180 degrees almost linearly. So this means we can fold almost any shape. And what is unique about our technique is we can also add some color. So although I showed mostly the black structures, we can also add color layers on the black layers. And then, for example, this is the example of the Earth. So usually people use a normal inkjet printer to print colors, and people use 3D printers to achieve a structure. But in this case, inkjet 4D print achieves both colors and a texture or shapes at the same time. So we're gonna talk about the software and design examples, but this is actually almost the same slides as I showed in earlier. So we actually extended the crane to achieve the inkjet 4D print technique. So in the forward design, for example, this is the example of folding, Miura folding. It is a super famous origami in the field of origami. So we can first of all fix the folding angle, target folding angle, and then the system generates the ideal ink structures. So the red one corresponds to the mountain fold and the blue one corresponds to the valley fold. So after this, we print the structure and achieve this kind of things. And actually, many origami researchers look at this and will be surprised and say, wow, or something. But because you guys are not such, maybe familiarized with origami structure, so these were all almost impossible to automatically fold in the past. Oh, for example, Yoshimura pattern is used for the hyoketsukan. Maybe if you go to the convenience store, you'll see this kind of can, because if you apply this kind of structure, it will increase the rigidity using the same amount of the materials. So like this, a lot of origami structure is used in the industry, and we succeeded in reproducing this kind of shape automatically. But we are not always the expert of origami. So we also have an inverse design pipeline. So in this case, you can input any 3D shape, and then a system automatically calculates the foldable structure. And as I showed previously, the system generates a printing pattern, but the printing pattern is much more complicated than before. But because it is not me to fold the structure, the basic pipeline is almost the same. So this is one of the examples of we folded using the inverse pipeline. For example, the bunny has more than 4,000 facets, or the cap has more than 300,000 facets. And as I explained earlier, it is known that any shape is mathematically foldable. That means maybe this method can also fold almost any shapes. But maybe one drawback is if you try to make an architecture, for example, the gravity can be an issue. So it cannot actually fold any shape, but theoretically it can fold any shape. Okay, so I'm gonna talk about the evaluation. So first of all, the resolution. So how small we can print this. So as a result, we succeeded in 3D print. So we succeeded in 4D printing the structure with the 3mm edges. And of course, this is more smaller than what we can fold by manual hand. So, and as a resolution, okay, I'm gonna just skip this slide. So this is a comparison between the previous methods. So in 2018, the maximum number of facets was 26, but we, for this time, succeeded in folding more than 4,000 facets. And as a maximum number of facets foldable, I mean, this number is for the bunny, and theoretically, we can fold more than 80,000 facets. So this also satisfies that this method can fold almost any shape. And maybe you're questioning why we are doing this kind of thing, because this is sustainable. Maybe we should say this is sustainable. So if you try to 3D print a rose like this, if you use a FDM 3D print, it will consume the supporting material 65 grams, and it will take more than eight hours. But if you use a 4D printing process, because everything is flat, you don't need any kind of supporting materials. And the total printing time is smaller than 1/20th of the 3D printing process. And I actually bring this kind of samples to so many places like America or so many places. But in that case, what I do is just, put a lot of sheets into the file. That's, super easy. So it is also really helpful for storage or maybe, shipping process. So I'm gonna explain some of the applications we can do. So for example, this kind of printing process can be really useful for fashion items. because yeah, as I showed earlier, we can fold complex shape using a Issey Miyake's please or steam stretch process, but that uses really large garment loom. So we cannot reproduce that kind of complex origami outside of Issey Miyake. But in inkjet 4D printing process, what we need is really normal UV printer. Maybe OIST also has a UV printer around here, I don't know. But yeah, you can do this really easily. We are using a normal ink and normal printer. And this is another example of a ship in a bottle. So in this case, we roll the structure into the bottle and pour the hot water to build a ship, which is larger than the mouth of the bin. So this is the example of the fabrication, even with a limited human access. For example, in the disaster, we cannot have access to the isolated places. But maybe if I apply this kind of method, maybe we can build a robot that can walk in the isolated places. But yeah, but somehow I made this example as a ship in a bottle. I don't know why. Yeah, anyway, so this is the last example of the interactive postcard. So in this case, this guy is posting the postcard and this lady receives it. And first of all, she has no idea what it is. But after pouring the hot water, she can tell, oh, this is a happy birthday card. So this kind of 4D printing process can also be useful for the interactive or encrypted messages. So this is the conclusion. Oh, this is so small. So inkjet 4D print enables self-folding of complex origami patterns with more than thousands of facets. And printing, yeah, we can achieve more than 20 times faster than the 3D printing without any materials waste in a smaller volume. And we can print both shapes and a texture in the same process. So we published this work in August in the last year. And later on, there was so many media coverage. And what I was so surprised about is when I was riding on a taxi in Tokyo, I saw my news in the taxi. So this is one interesting moment for me. So, okay, anyway, this is the end of the inkjet 4D print. So conclusions. So I'm working on computational fabrication. So computational fabrication refers to the combination of computational design and the digital fabrication, which is an emerging topic after 2010. And I'm mainly focusing on origami-inspired computational fabrication. So 3D printing plus origami, design plus origami, or fabrication plus origami. So I'm not sure how many people are interested in fabrication, but you can take something away about origami at least. Okay, this is the end of my talk. Thank you.